last time oh, yep, got it. Yeah, the last time I was at Carnegie was many moons ago, probably like 2013 or 2014. So it's great to be back to talk to you all about rare massive galaxies in the early universe. My primary focus, as many of you know, is in the obscured universe, just looking at dust and gas. But of course, with the arrival of James Webb, that is expanding somewhat. And so I want to share with you today some of our planned exciting projects to be pursued with Webb. So, get going here. Does that work? Yeah. Okay, so I'm splitting the talk in these two parts, focusing on the tremendous capability of both Alma and James Webb for pushing massive galaxy science in the early universe. And so on the one hand, Alma, of course, exists and is here. I mean, Webb, of course, exists, but is not yet usable. Alma has been in, full-flung mode for several years now, a decade since it saw first light. And so where are we in our understanding of massive obscured galaxies in the early universe from Alma? I'll touch on that. And then, where do we want to go? What are we wanting to focus on with Webb to push this even further? So I'd like to show this rendition of the cosmic star formation rate density. It's a bit different from, the standard Maddow and Dickinson review, that we see. And the reason I like to show this is it splits up the components of the star formation rate density into obscured and unobscured components. So you see the rest frame UV and optical samples of galaxies shown in blue, which of course we've done a tremendous job of taking census of to the well beyond the beginning or the end of reionization into the first gigayear of the universe, all the way out to redshift 11 or so. But we're playing catch up in terms of taking an accurate census of the star formation rate density contribution from obscured emission. So this includes galaxies that are predominantly obscured and have very little light leaking out in the rest frame UV, but it also includes, of course, the contribution of galaxies that you might select as Lyman break galaxies and how much emission they're actually outputting in obscured tracers, so in the infrared and submillimeter. So with Alma, of course, we're trying to solve this puzzle of what the star formation rate density looks like at early epochs, basically from redshift 3 and beyond, because that is kind of the era where various literature works start to break down and disagree with one another quite substantially. And so we really want to understand the role of obscured star-forming galaxies, in particular, in driving galaxy growth in the first 2 gig years. And we just have very little understanding of that. And then, of course, with Webb, we want to push much further and do a better job in unobscured tracers at earlier epochs. So I'll start off with Alma, since that data is in hand and real. And I just wanted to, emphasize, I know there are some Alma users at Carnegie, but I think it's really impactful to take in the breadth of the impact of Alma across extragalactic studies to date. And so these are really quite varied and are really remarkable. So, as just a snapshot of some of these results, Alma has been able to resolve very detailed ISM kinematics in high redshift lensed galaxies, This is showing, the very long baseline campaign data, which, I hope you've seen. It's really a remarkable Einstein ring. But not only are we able to study the resolved ISM kinematics on, the scale of giant molecular clouds and redshift 4 galaxies, the background, we're also able to study the foreground structure and piece together whether or not there's detection of dark matter substructure in systems like these. Completely different result is the detection of tidal tails in mergers beyond a redshift of 4. This is something that's virtually impossible to do with Hubble because of surface brightness dimming, whereas with Alma we have a huge advantage of not having those same dimming effects due to the very negative K correction looking at dust emission. So there have been really remarkable detections of tidal tails beyond redshift 4. We've detected molecular outflows at redshift 5, large reservoirs of molecular gas being expelled from galaxies in highly unstable systems. I mean, these are quite remarkable galaxies. There's also been detections of molecular gas in galaxies that have only been detected in absorption. So these are, damp Lyman alpha systems that now Alma can follow up and detect in molecular gas and learn more about. We found some of the most massive extreme galaxies beyond a redshift of 6. So there's been a detection out to redshift of 7 of an extremely massive system detected by the South Pole Telescope and confirmed through Alma. We've resolved spiral structures in arms and bars of individual systems at redshifts 2 to 4. And then, possibly, most exciting to the broad audience is that Alma has been a really useful tool for actually spectroscopically confirming very high redshift LBG candidates that are found through Hubble and will be found through Webb. And it's doing this by detection of far IR cooling lines like C2 and O3. And so, the most secure highest redshift sources that have been spectroscopically confirmed come from Alma. So that's a very exciting use case for Alma in extragalactic science. So this kind of gives you a snapshot of how Alma has been really transformative for individual discoveries. Lots of really interesting case studies of individual galaxies, but what can we learn from Alma by pushing our knowledge of aggregate populations of obscured galaxies at early times? And so this has been, something that I've been focusing on for quite a while. Maybe you have digested these results already, but what I'm showing on the right here is the results from the ASPEX large program. This is the first large program in extragalactic science with Alma, and it resolved to map the ultra deep field at millimeter wavelengths, at several millimeter wavelengths, and also taking 3-dimensional data through spectral analysis of the field. But if you look at these two images, on the left and then on the right, what immediately strikes you is an absence of galaxies on the right in the Alma image, a dramatic number of sources in the ultra deep field, of course, but we're not finding those. We're not detecting them in dust continuum with Alma. And so this has naturally led to, a question stirring in the community of why are there so few dusty galaxies? A obvious hypothesis is posing the question, are early galaxies somehow devoid of dust? And this has largely been the message that's been kind of propagated by my friends in the UV, in the rest frame UV, Lyman break galaxy community, searching for high redshift galaxies. And that's, kind of distilled in these two plots of the star formation rate density shown here from Steve Finkelstein's paper and also Richard Bowen's, showing that split contribution of a dust corrected star formation rate density and an uncorrected star formation rate density, and that the two largely converge in the early universe. And so this leads to the question, are there dusty galaxies in the early universe? The consensus of the broader community, I would say, given these Alma deep field results, has been, well, no, there's an absence of dust at early times, and it seems like that is on the surface the correct conclusion. But I'm going to suggest that we are simply looking for dust in the wrong places here. And so, as a reminder, dust preferentially lives in high mass galaxies. I mean, dust is, of course, present in a variety of environments and is present in low mass galaxies as well. But the tremendous impact of dust on the spectral energy distribution of galaxies really kicks in at high stellar masses. So this is a plot from Kate Whitaker's 2017 paper, in which we showed that as a function of stellar mass over a fairly wide range of epochs from redshift 0 to 3.5, the fraction of the star formation rate that's obscured by dust steadily increases with stellar mass, such that above 10 to the 10, you have 80% of your star formation obscured by dust, and at higher masses, you're approaching 90-95% of stellar mass is obscured. This just shows you the same conclusion projected on the stellar mass star formation rate plane, just showing you the origin of the measurements of star formation rate, whether they be from unobscured tracers or obscured tracers. And what you see is at the high mass end, almost all of the star formation is traced through these obscured tracers. And so, but of course, we know also that at the high mass end, those galaxies are much more intrinsically rare than galaxies farther down on the luminosity function. This just shows you a snapshot at right here of the luminosity function of galaxies projected onto a star formation rate function at redshift 2.5. So you have your Lyman break galaxy population that falls off steeply at very high star formation rates. And then dusty galaxies pick up at those very high star formation rates. The luminosity function is very different for dusty galaxies than for unobscured systems. The characteristic luminosity is much higher. The faint end slope is much more shallow than it is for the UV luminosity function. But it really dominates these sources at the bright end. And of course, there's something like a factor of 100 difference in number density of Lyman break galaxies and dusty galaxies. And so that's really critical to our understanding of, those Alma deep field results from in the ASPECS program, because dust will preferentially, live in these very high mass galaxies. Pencil beam surveys just will not see them, and they're not well suited to detect them. So, my interpretation of these plots that we have, the star formation rate density and the obscured and unobscured component, what they say is that they, the plots don't tell us that galaxies are less dusty at high redshifts. They aren't able to really comment on the relative, abundance of dust in individual systems, and whether or not those are different at redshift 8 than they are at redshift 4 or redshift 2. Instead, what they tell us is that there's a perceived absence of very rare extreme galaxies at redshifts greater than 4. And these extremely rare, extremely dusty systems happen to actually dominate cosmic star formation at the peak at redshift 2. Those are, ULERGs at redshift of 2. These are sources that are very luminous at Herschel wavelengths. That's a natural consequence that these extreme dusty systems dominate cosmic star formation around a redshift of 2 by virtue of galaxies' star formation rates being much higher at that epoch than later in the universe's history. So this is kind of the landscape of claims with respect to, how dusty the early universe is. I'm going to make the argument today that we've done a pretty bad job of searching for extremely rare sources beyond a redshift of 4. So why should we care about extremely dusty sources beyond a redshift of 4? I think, the more I think about this and the more I kind of try to take myself outside of my bubble community of folks who really care about millimeter galaxies is that, a lot of our understanding of what pushes the limits of galaxy formation and evolution comes from the population of what we infer are the most massive halos at early times. So for example, rare quasars have been used for quite a while to calibrate our understanding of massive halo formation in cosmological simulations. Dusty star-forming galaxies have been rather absent on the scene in terms of being useful tools like quasars. And that's because we've not really found many at very early times compared to quasars, that have been known out to redshift 6, 7 for a while now. But they are pretty useful. So dusty star-forming galaxies, this population of rare extreme systems, are often actually more massive and more numerous than rare quasars. And the reason they would be, of equal mass or slightly more mass, but also more numerous, is they have a longer duty cycle. So we see them in this elevated phase of a very high star formation rate, longer than you would see rare quasars in this elevated state. So they can be, very useful calibration tools for understanding, how physics is pushed to the limit in terms of the formation of early massive systems. So, but beyond just understanding massive halo growth, their dust reservoirs are also extremely puzzling. So the formation of their dust reservoirs is unclear, particularly in, less than a gigayear after the Big Bang. And the reason that is dust production mechanisms shortly after the Big Bang have, fundamental time limits, whether dust comes from AGB stars, is limited to ISM growth, or whether or not supernovae can produce sufficient amounts of dust that we actually measure in these systems. This is showing at right here an example from the SPT survey, SPT 0311. It's a system that has a star formation rate of 3,000 solar masses per year at redshift 6.9. A tremendous gas mass and over 1 billion solar masses of dust. And so the formation mechanism of that dust is quite puzzling. So in theory, for those of you who followed some millimeter galaxy research over the past 20, 25 years or so, finding very high redshift obscure galaxies is where submillimeter surveys shine. They are optimally designed to find this population. This plot, the map and the plot are shown, those are from the original works on the Hubble Deep Field from David Hughes in 1998, showing the original scuba map. And the implied star formation rate density contribution of these scuba detected galaxies. And the reason this field really took off is because it was astoundingly high. The number density of detections, you know, good luck identifying individual sources in this map. The number of individual detections, though, however, implied that there was a really tremendous contribution of highly obscured galaxies at early times. But, you know, and the reason submillimeter work is so useful for this is that we have a really unique advantage compared to other wave bands in astronomy, and that is because the submillimeter regime has a very negative K correction, not just a negative K correction, but a very negative K correction. So here I'm showing you an animation of a galaxy's spectral energy distribution, albeit a pretty dusty one, but the same effect, you know, is there whether or not it's dusty. And I'm pushing it back in redshift. So it has fixed luminosity and I'm pushing it back in redshift. And what you can see, I've sampled the SED at 3 different points, one in the optical, one in the near infrared, and one in the millimeter. And you can see on the right, the plot of the observed flux density as a function of redshift. And predictably, the near infrared and optical drop like a rock. You need very sensitive telescopes to find sources at high redshifts. And those regimes, but in the millimeter, it's roughly constant with redshift. So if there are highly obscured systems to find at high redshifts, say beyond redshift of 5, you don't need to go super deep to find them. They should be in the maps because their flux density is roughly constant with redshift. But that's a double-edged sword, of course, because with flux density constant with redshift, you also have great difficulty constraining redshifts. So that's going to be my very quick summary of the last 25 years of submillimeter galaxy work, is that we're pretty lousy at inferring redshifts, getting redshifts for submillimeter luminous systems. And it turns out that those redshifts matter a lot. Particularly as we push towards higher and higher redshift regimes. Just to show you some examples of that, here are 2 submillimeter galaxies, dusty star-forming galaxies, who have claimed redshifts in the literature of redshift 1.4 and 1.1, but it turns out with more detailed scrutiny of these sources, their redshifts, you know, on the left-hand side are actually unconstrained, still no redshift for that source. And on the right, the redshift is now confirmed at 4.6. And these subtle misidentifications, you might figure they don't matter for individual sources in a very large sample of hundreds of these, but they actually do, because we expect the tail of the distribution for very high redshift systems to be not that populated. So if you have misidentifications on a 5% level of your entire population, that washes out all constraints on the redshift greater than 3 obscured universe. And this has led to dramatically different interpretations present in the literature. So here I'm going to consider, you know, 2 hypothetical universes, a dust-rich universe and a dust-poor universe, which is just a simplification of the, you know, the integrated volume density times star formation rate of the obscured galaxy component. So you could imagine in these 2 dramatically different interpretations, here, what drops like a rock would be a dust poor universe. That dusty star-forming galaxies at redshift greater than 4 are insignificant. Several papers have claimed that, and that has been well measured. And then on the flip side, there are other works that claim that actually dusty star-forming galaxies dominate all of cosmic star formation, even beyond a redshift of 4. So that would be a dust-rich universe. And what's remarkable about this is, in some modeling work that me and my group pursued a couple of years ago, is we found that the difference between these two dramatically different universes would only result in a couple percent difference in, how many 850 micron selected galaxies sit beyond a redshift of 4, like 3% and 7% of a population. So it's a really minute difference, and we haven't gotten anywhere near that level of precision in constraining the population. And so as a result of that modeling work, we sought out a way to improve the measurements and constraints of the star formation rate density at early times from obscured galaxies. And so we embarked on this program called Mapping Obscuration to Reionization with Alma, or the MORA program. And the MORA program is a large collaboration within Cosmos that is led by both myself and my former postdoc, Jorge Zavala, who's now staff at NAOJ, and my former graduate student, Sinclair Manning, who's a Hubble Fellow at UMass this year. So this work from the MORA survey is published all this year in Jorge's paper, my paper, and Sinclair's paper that have all been posted to archive. And the goal of MORA is to basically take a measurement, a direct measurement of the star formation rate density from obscured galaxies alone beyond a redshift of 3. And how we did that was we constructed this large deep field map with Alma at a wavelength of 2 millimeters. And it's roughly the size of the candle's footprint in Cosmos, if you're wondering. Just to show you the relative size of MORA with respect to other Alma deep fields, we have the UDF here in the center, the GOODS Alma project, and then also the pilot ASPEX project shown here. So those are the extragalactic deep fields that have been mapped with Alma so far. So why did we do 2 millimeters? It turns out that 2 millimeters is uniquely useful for filtering out lower redshift obscured galaxies, which is really critical when you're trying to make a precision measurement of the higher redshift contribution. So here I just traced out in a thick red line the negative K correction with at 2 millimeters. So this is a plot of just flux density for a galaxy of fixed luminosity, fixed SED with redshift. And you can see that remarkably at 2 millimeters, you see an inversion such that galaxies of fixed luminosity at redshift of 6 will be brighter than those at redshift of 1. And so if you tune your sensitivity carefully, you can effectively cut out the redshift 1 to 3 sources and exclusively aim towards higher redshift regimes. And so this is showing you various model predictions of what we would find in a cumulative redshift distribution plot. So some of the, this is showing the star formation rate density and different colors map to the same colors in this cumulative distribution. If the universe is extremely dust rich, then we'd see a very high number of sources that extend out to high redshifts. And for a dust poor universe, you'd see very few sources and an overall lower average redshift. And so what we found in MORA is the following. So the black distribution shows the redshift distribution. And these data effectively rule out the dust-rich case that, you know, there isn't a entirely dramatic population of dust-obscured systems at redshift 4, 5, and 6 that we just haven't found yet. But there are quite a few systems that we still haven't found, and they are relatively rare, but not as common as some works predicted. The redshift distribution skews a little high compared to several models, and so, you know, further data would have to constrain that more. And thankfully, MORA, we did get an extension for Alma cycle 8 to expand the area by a factor of 4. And so hopefully with more extensive data, we'll be able to comment on that skew in redshifts and also find many more systems beyond a redshift of 4. So the nutshell of this work, the conclusion is that 2 millimeter selection does a very good job of finding these very high redshift DSFGs. 75% of the population is beyond a redshift of 3 and 30% is beyond a redshift of 4. That might not sound dramatic, but it is actually quite constraining for how the infrared luminosity function evolves at early times. Just to show you a quick snapshot of some of the sources we found. Here's a source at redshift 3.5, and you can see on the left 3 panels, those are deep HST images from both Cosmos and candles. And you can see that sources are almost uniformly not detected in these almost 2 millimeter sources are not detected in deep HST imaging. Some of the redshifts we still don't, you know, have good constraints for and are pursuing further follow-up. But there are these interesting case studies embedded within the MORA map, like the redshift 4.3 source that was mistaken for 5 years as being a redshift 1 source. And also another source that was unconfirmed spectroscopically for 10 years, and it wasn't particularly of interest to anyone, but is now spectroscopically confirmed at 5.85, and at the time was the highest redshift unlensed dusty galaxy. And then we have some others that have unconstrained redshifts, and they're also, quote, HST dark, so they drop out of deep candles imaging, but are detected by Spitzer. And so those have been the focus of my former student's paper, Sinclair Manning, who's now a Hubble Fellow at UMass. So I'd encourage you to check out her paper where she characterized these as best we can as redshift 4 progenitors of massive quiescent galaxies. Just to show you a bit more, just briefly about this redshift 5.85 source as the most distant unlensed dusty star-forming galaxy. What's really useful about this, the fact that it's unlensed, means that we have a really good constraint on its volume density. And, you know, that sounds somewhat boring, but it's actually really critical for understanding how common these are at redshift of 6. And also, that volume density estimate is really crucial for calibrating measurements of its mass. For example, this source, if you had no idea how common it was, we would have inferred that the stellar mass might have been much, much higher than it actually is. We were able to rule out some models that suggested the stellar mass is quite high based on the fact that it would be extremely unlikely to find a galaxy of those masses within the volume limit of our survey. And so systems like these, it's a merging pair of galaxies at redshift 6. We have further follow-up data in Alma cycle 8 to give us a much more detailed high-resolution look at dynamics through C2 of systems like these. But also, we're really excited to find more systems like these in the extended MORA survey coming up this year in cycle 8. The last thing I want to share with you from Alma is these results from Jorge Zavala's work, where he used a really innovative technique using the number counts. So just, number of sources per flux density on the sky at both 1 millimeter, 2 millimeter using MORA, and 3 millimeter using archival Alma searches to constrain the infrared luminosity function out to redshift 6 and 7. And so this shows you the gray here are the variety of models that exist from dust poor to dust rich universe at 1 millimeter, 2 millimeter, and 3 millimeters. And you can see that the breadth of predictions is rather narrow at 1 millimeters, but widens significantly at 2 and 3 millimeters. And so if you collapse those onto the most likely cases of the infrared luminosity function, what you see is a really careful calibrated constraint on the total contribution of obscured star formation out to redshift 6. So this is kind of the culminating plot showing for the first time we have these reliable measurements out to redshift 6, 6.5 of the star formation rate density in Jorge's paper. And the main conclusion of this work is that we find that the dominance of obscured emission in the star formation rate density really only picks up at redshift 4 to 5, and then of course goes on to dominate towards redshift 2. But these early epochs are indeed, we think, more dominated by unobscured emission. And you can think about the contribution of these rare dusty systems, much like quasars. Their volume density actually traces the volume density of quasars pretty closely, shown here in the black line for quasars and this red patch for these extreme luminous population. And so in thinking about the population like quasars, I'm excited for the next stage of finding more sources like these. I think, there's huge potential for single dish submillimeter observatories like the Large Millimeter Telescope and GISMO to find these extremely rare systems at early times and use them much like the population of quasars to calibrate the formation of massive galaxies. Okay. So with what little time I have left, I want to share with you our plans for continuing to look at massive galaxies in the early universe through Cosmos Web. So very excited this was approved, and kind of still remarkably in disbelief that Cosmos Web is happening. It's a so to show you a map, this is a collaboration within the Cosmos team. Of course, that's been going since the original ACS data of Cosmos were taken 15 years ago. And so here we're showing the large ACS mosaic, almost 2 square degrees in Cosmos relative to the scale of the moon. Cosmos Web will continue that legacy of building up really extraordinary data sets in this field by producing continuous near-cam imaging over the central 0.6 square degrees and 4 filters, and then also map in parallel with MIRI over an integrated 0.2 square degrees. And you can see the MIRI pointings here are shown in red relative to the blue area shown for NIRCam, and we have a few MIRI pointings we had to actually flip by 180 degrees for observability. But currently, this is the observing plan. I wanted to show you a simulation of Cosmos Web in RGB in 3 of the 4 filters that we'll have with NIRCam actually simulated at the depths of our program. This was prepared using the deep realistic extragalactic model, or the DREAM work convolved with a realistic JWST PSF, and this was created, the simulation was created by Nicole Dracos and Bruno Villaseñor at UC Santa Cruz. So here's a little animation just showing you the UDF as it exists, and then what we expect to see at that scale in a simulated JWST Cosmos Web level depth image. But of course, Cosmos Web will be much larger, and so we are really thrilled about the scale over which Cosmos Web exists. So zooming out some more. So that line there is about 10 arc second, or it's 10 arc minutes across, excuse me. So that's just showing you the scale of what we plan for Cosmos Web relative to UDF and the moon. So what we'll find in Cosmos Web, it'll have about 1 million galaxies detected down to magnitudes 27.5, 28, a little beyond 28th magnitude with NIRCam. And in the MIRI data have something like 32,000 galaxies detected at 7.7 microns. And so we're really thrilled about this data set. A question that we often hear is why we would propose something so absurdly large with Web when we can go much deeper. We have 3 primary goals of Cosmos Web, the first being reionization, the detection of thousands of galaxies from redshift 6 to 11, to really constrain the bright end of the luminosity function and measure the patchiness of reionization itself. Second, we want to detect quiescent galaxies at redshift 4 to 6 and find hundreds of those and constrain their formation mechanisms through detailed resolved work. And then last, we would like to use these observations to calibrate the stellar mass to halo mass relation using weak lensing. So with these data, we'll be able to do that out to redshift 2.5 or so. You know, that it's another reason for having such a big field of view, and it will be useful for future calibrations of Roman and Euclid weak lensing efforts. Just to really briefly touch on the reionization science only here, cosmological simulations really indicate that reionization is a patchy process. This simulation is a snapshot of the redshift 7 universe. Pink is showing ionized IgM and neutral IgM shown in blue here. There are clusters of massive galaxies, you know, shown in lavender circles here. And you can really see the motivation for mapping an area this large when you superimpose the field of view of JWST GTO programs and also the other ERS programs, including Sears and Cycle 1 program, including Primer, that all of their collective fields of view don't add up to what we're planning to cover with Cosmos Web, and would struggle to capture these really high density unique environments. And reionization, we think, was a patchy process. Its midpoint is constrained to be around 7.7, around redshift 8. It finished, we think, around redshift 6, but its beginnings are largely unconstrained. And so that is a major goal of many of these deep field projects, is to constrain the beginnings. But the patchiness itself is best constrained through a program like Cosmos Web. And this is one of our goals. So here I'm just showing you, hints that we have that the process of reionization can be indeed very patchy. So this is some quasar sightlines. You'll see these tremendous Gunn-Peterson troughs extending beyond a redshift of 6 when we think reionization ended, with large patches of neutral IgM down to redshift 5.5. And similarly, simulations suggest reionization would be quite patchy. And so you're not going to be able to measure that in small fields of view that are highly prone to cosmic variance. And so Cosmos Web really surpasses that by exceeding a half a square degree, which is largely the scale that we expect that patchiness to exist on. And then, the big question here is which galaxies drive reionization itself? Is it the low mass galaxies or high mass galaxies? So this is showing a cartoon plot of ionizing how ionized the universe is as a function of redshift. If the process is dominated by low mass galaxies, you might expect to see an ionization fraction that is more slowly ramping up versus something that basically transforms the universe very quickly from high mass galaxies. Constraints from Planck only give us the snapshot of an instantaneous reionization redshift from the measurement of tau. But there's a lot of uncertainty here. So models disagree. There's a lot of details I'm not going to talk about, but massive galaxies or low mass galaxies, it's still unclear which population dominates. And so Cosmos Web here exists to really probe that high mass end and see how dominant that population might be at contributing to reionization. And this is just showing a snapshot of the luminosity function from Rebecca Bowler's work in 2020 from ground-based efforts to measure the tip of the luminosity function. And you see, the suggestion that it perhaps deviates from a Schechter function at redshifts 8 to 10, which is tantalizing and, but really requires data like Cosmos Web to nail down. And of course, to actually measure whether or not these galaxies live in ionized regions requires spectroscopic follow-up, pursuing Lyman alpha in particular, that would resonantly scatter off the IgM in a neutral medium. And this is really a prime use for GMT that we're excited about. The Cosmos Web filter set will have really broad use beyond reionization. So this is showing existing data in the Cosmos field, these little bars and their depths across as a function of wavelength, and where Cosmos Web sits relative to those. You'll see the F277W filter goes uniquely deep, and then MIRI filter is out here at 7.7 microns. This is my last slide before my summary. So we really hope that the community makes broad use of Cosmos Web, and I'm sure they will, but just to highlight some of the legacy projects that can be pursued with Cosmos Web, we'll have galaxy morphologies up to redshift of 6 on, and also beyond, but, a tremendous number of systems will have this really detailed, unprecedented morphological analysis available to, track the role of interactions out to very high redshifts and constrained size mass evolution. We'll also have rest frame near-infrared morphologies through the MIRI data of 32,000 galaxies. And so that'll be really nice pairing with the NIRCam data. we'll be able to spatially resolve SEDs of galaxies and, produce maps of star formation rate, mass, dust maps for many systems. Actually measure evolution of the dust attenuation law through combining with long wavelength data. We'll be able to identify hopefully some black hole seed candidates from very early epochs that are predicted to be extremely rare, but could be found in a field of view like Cosmos Web. Study the coevolution of supermassive black holes and their host galaxies. And then kind of more further afield from run-of-the-mill XGAL, but quite exciting, is to search through the data for the highest redshift supernovae, comparing to existing data that are taken at different epochs than Cosmos Web. And so, there are discussions about whether or not we want to perhaps pursue another epoch of imaging across parts of the field. And then, even within the Milky Way, we'll be able to detect ultra cool halo subdwarfs. The filters that we have are uniquely useful for looking at and discerning low mass stars in the halo out very far to something like 10 kiloparsecs. So we'll be able to find those in this image if they are there, and then characterize those low metallicity systems in the Milky Way halo. Okay, so just to summarize, Alma and JWST will be really incredible. Well, Alma is already incredible to constrain massive galaxies, rare galaxies in the early universe. I shared with you today our 2 millimeter focused efforts of filtering out foreground dusty sources to really make the first reliable constraints of the redshift 4 to 6 star formation rate density from obscured tracers. So that was from the MORA survey, and those results are published in these papers. And then, I think we're all very excited to see the launch of James Webb, and me in particular. My primary interest is in this large program, Cosmos Webb, that I'm very excited about, and will hopefully serve as a tremendous legacy data set for the broader community. Thanks.
I'll clap for everybody. Thank you so much, Caitlin. So yeah, I already see hands raised. So let's see. Shengyi, do you want to ask your question?
Hi, Kathleen. Thank you so much for this exciting talk. So I'm not very familiar about the dusty galaxy measurement. So I just want to double check I understand. Is it correct to say that if a high star formation rate galaxy is very dusty, then it will be bright on the 2 millimeter, but very faint for sub-millimeter lines like C2 or O3, because dust will reabsorb them. But if a high SFR galaxy is poor in dust, then the observation will give you results the other way around.
That's a great question. That kind of goes a bit beyond what I talked about, but I think so those far IR cooling lines like C plus and O3, those lines are turning out to be tremendously bright. You can have something like 1% of the luminosity of the system come out in those lines. And so there is some suggestion that you see lower like C2 to far IR ratios in the most luminous IR galaxies, and that could be due to self-absorption, like there's happening near the peak of the SED. But by and large, we still see that line quite. It's pretty rare when folks have looked to not find it in a source that is securely spectroscopically, constrained, and I think by and large, cases where you're not finding C2, a large fraction of those will end up being, not at the right redshifts or something. And so I would say it's by and large going to be there, even if it's suppressed in these very dusty systems, because LIR is also quite high, and so the luminosity of C2 will still be high. Yeah.
I see. Yeah. So my following question is about, so do you think it's possible to use those 2 millimeter measurement, maybe also combine with the C2 and the O3 measurement to constrain the amount of dust, something like the dust to metal ratio for those high redshift galaxies?
Yeah, I mean, that's a great question. I think the use of far IR cooling lines to do metallicity measurements in obscured systems is really exciting and hasn't yet really taken off properly, and the reason that hasn't taken off properly is probably given the difficulties in calibrating it relative to, metallicity measurements that we actually have available to us in the rest frame optical, and that is largely limited to the local universe right now. But I think once web data comes, we'll be able to basically ramp up the use of Alma for measuring metallicities too, and calibrating that pretty well. In terms of measuring the overall dust mass, I mean, I think metallicity is kind of key to understanding the overall dust mass that is there. And I think, I think that is probably one of the most promising ways of going about constraining that. I mean, we, in theory, can measure a dust mass directly from the far infrared dust continuum. But of course, that depends on, the dust characteristics being relatively, constrained to what we understand them to be in the local universe. And so any deviations of that will, of course, need far more data than we have now.
Yeah, so finally, I have a pretty trivial question about the the star formation rate density measurement. So can you quickly say why the UV, the IR seems to give much higher SFRD than the UV measurement, especially at the low redshift?
Oh yeah, that's a great question. I mean, basically, when you see other renditions of this plot, you just see like, oh, dust agrees with UV, and what that is true, but that's after UV has been corrected for dust attenuation. So basically you can, these two curves that I'm showing here are roughly like a factor of 5 difference. And that just accounts for the galaxies that are detected here in the UV constraint have that maybe only 20% of their light is coming out, in the UV, and 80% of that is obscured.
Okay, so this doesn't include the correction for...
Yeah, so it's basically avoiding the double counting that you often see in the plot. Yeah. Mm-hmm.
Okay, thanks. Those are all my questions.
Yeah, great questions.
So we probably have time for 1 or 2 more questions if anyone has them. I have a question. So massive galaxies definitely have more dust, which obscures star formation. But will you be able to say anything about the characteristics of the dust, and especially the geometry of the dust within the galaxy, and how that affects how much star formation is obscured?
Yeah, I mean, you've hit on a very important point that I didn't even talk about, which is the dust geometry. And dust geometry has a tremendous effect on the output of galaxies in the rest frame UV and the long wavelengths as well. So I mean, I think a key of getting disentangling effects of geometry is getting high resolution data. Of course, Webb will give us the high resolution data on one end, spatially resolved, morphologies and understanding clumpiness, and then I think in parallel we can do this high resolution follow up with all the sources from Alma and have that one-on-one comparison to infer the impact of geometry. But absolutely, I mean, geometry is dust geometry, particularly in these systems where you have tremendous, massive galaxies. You often have very messy morphologies and interaction histories, and that is reflected in messy dust geometries relative to star forming regions, for sure.
Yeah, that's really exciting. I'm looking forward to that eventually when that comes out.
Yeah.
Okay, so I think we'll call it a day, and just want to say thank you to Caitlin again for such a great colloquium, and everyone have a great rest of your day.
Thank you.
Thanks.
See you in a bit, Caitlin.
Thank you.
Yeah.
See you in a few.
Yep.